right, well, thank you everyone for coming today. I think this is going to be a very, very interesting talk today. Of course, all of us at NSIDC are, of course, very, very interested in sea ice. It's one of the things that we do. And of course, a lot of what we're interested in is the science questions about losing sea ice and things like that. And of course, there's a number of us scrambling right now because we had some problems with our data feed and some dropouts, and we're still trying to scramble with that. And we've already gotten a plethora of emails from people wondering what the heck is happening. Right? But we must remember that the sea ice loss, what's going on, is of high interest to operational agencies, people who operate up there, who need this information. And so today, I think it's great because we have that perspective coming in. And here I'm going to introduce, I want to get it right, Mac Ortiz. You go by Mac Ortiz from the National Geospatial Intelligence Agency. And we have Alex Darden, okay, who is from the U.S. National Ice Center. Of course, we work with the National Ice Center, as you probably know. And so we're going to be learning about leveraging automation for sea ice mapping. We can always do better with sea ice mapping. So we're going to hear the latest on what is going on. So with that, I believe, Mac, you're starting out here. And so take it away, please.
Thank you. So good morning to you guys. Thank you for having us. My name is Mac. I'm currently a research scientist and program manager at NGA. And I'm the PI of the work we're going to show today. I've been with NGA for about 2.5 years or so, and my main focus has been on developing R&D programs that blend machine learning with cryosphere processes. So now I'm going to pass this along to Alexandra to introduce herself.
Hey, good morning. I am Alexandra Darden. I am currently a Master Ice Analyst at the U.S. National Ice Center, where I have been for about 5 years, and am part-time detailed to NGA to assist in the work that Mac and I will talk about today. And with that, I will pass it back to Mac to begin the presentation.
Thank you. So as the title says, today we're going to present work on an NGA-NIC collaboration that utilizes automation and machine learning for sea ice mapping. The motivation behind this is, we know that the Arctic is rapidly changing, but also the fact that, within 5 years, the commercial SAR sector will have about 400 or so small SAR satellites in space, which is going to make sea ice analysis and imagery extremely impossible without the aid of automation of some kind. And just a shout out to my team here. We have a plethora of computer scientists, mathematicians, physicists, and we are working very closely with the Aerospace Corporation, who have done an amazing job with this. And that, next slide, please. All right, so although a variety of satellite sensors used for sea ice mapping include not SAR, one of the most prevalent sensors used is this synthetic aperture radar sensor. The reason being why SAR is so widely used for this type of work is that there's no solar radiation required, since this is an active sensor and it uses its own source of illumination. So we're able to image over the Arctic and Antarctic during winter months where there is no or little sunlight available. We also know that the Arctic is a rather cloudy place, especially during the summertime. And so SAR operates at a particular wavelength where it can penetrate through the clouds. SAR sensors have the ability to send energy to the ground in different polarization modes. And these type of polarization modes can discriminate between different ice types in the ocean surface if you use those combinations. And finally, most of the SAR sensors out there and in the future are going to be polar orbiting or near polar orbiting. So we're going to have excellent coverage in those areas. Next slide, please. So how does SAR work? We can simply look at it as a it's a radar for rough surfaces. So if we start with the graphic on the left-hand side, the SAR sends pulses of energy to the ground, depicted by that transmit arrow that you see. And if the surface is very rough on the ground, the pulses of energy will interact with the surface and be scattered about. So by the time that the satellite moves just a little bit in flight direction, the signal received will be a sum of various rough materials on the ground, and will look very bright in an image. So rough equals bright. Now, on the other hand, the figure to the right, if the SAR image is over a very smooth surface, like a calm body of water or a paved parking lot, that smooth surface acts like a mirror, like a Lambertian surface. And instead of scattering the energy in all directions as a sum back to the receiver, those signals get scattered directly away from the receiver, and that signal is essentially lost. So that part of the image will look very dark and almost black. And this is a very simplified version of how it actually works, but for the most part, this is, just take it with a grain of salt, but this is sort of the main idea. Next slide, please. So this slide depicts a SAR image versus a panchromatic. The SAR is on the left-hand side, and on the right is a declassified pan image taken over the Beaufort Sea. And these two images have been taken about 4 hours apart or so. So the SAR on the left is about a 1 meter resolution per pixel. I'm sorry, it's about 3 meters per pixel, and the panchromatic on the right is about 1 meter. And you can notice with the SAR, the calm bodies of water are very dark, like I mentioned before. And the ice, specifically over the ice ridges, which are very rough, are bright because of what I mentioned. These rough surfaces are scattered as a sum to the receiver. And you can see a lot more structure to the SAR. The ice ridges pop out more, and you see different shades of gray as opposed to the optical image. However, the optical image is a great image for sensing higher resolution features like ponds and fractures. And a little bit more about the SAR is really a difference between something called volume scattering and surface scattering. And I won't go into detail about that, but certainly you can ask me about that later. Next slide, please. So for our study, we used 2 data sets. One is a TerraSAR-X. It's a German commercial SAR. And on the right hand, you see RadarSat, which is a commercial Canadian. The TerraSAR-X is an X-band radar, which is higher frequency than the C-band. And the TerraSAR-X that we used was in strip map mode, which is at about 3 meter resolution. And the wide scan SAR mode is each pixel is about 50 meter resolution. And so you can see that the strip map is much higher in resolution. You could see more features, but the RadarSat 2 gives you a larger area coverage. So it's good to look at like ice edge, for example. Next slide, please. So deep learning techniques. Our goal was to segment the pixels in the SAR image into sea ice pixels versus open water pixels. And we wanted to do this in an automated fashion. We tested out 2 different types of machine learning techniques. One is called supervised learning, and the other one is called unsupervised. So supervised methods require labels, while unsupervised methods do not require labels. For the supervised method, we decided to use a specific convolutional neural net, which is a neural network that uses convolutional filters called UNET. For our unsupervised method, we used a variational autoencoder, which we then fed into a clustering technique. And I'm going to get into more details about these in the next slides. Next slide, please. So for the UNET, we used, for the supervised, for the UNET model, we used about 130 labeled RadarSat 2 images, where we took 2,000 image chips of a size 224 by 224 for training. And then we used 30 images as a whole for testing. The labels were ice, no ice, meaning ice and open water. If the ice was a very dark color in the labeling process, we attributed this as open water. And we also used real backscatter values from the radar, meaning we used calibrated signals from the radar and not something called the magnitude. The graphic you see below shows a test image on the left-hand side, which is an image that the neural network has never seen before. Before it gets segmented into these ice probabilities as an output. This technique allows for more control over the results because you can threshold to your liking. The pixels with a yellow color are more likely to be class ice, while the deeper blue pixels are more likely to be water. And there were some processing steps I'm not showing here, but for the sake of time, because a UNET works by feeding image chips in blocks, the ice probabilities, they come out in a blocky sort of appearance. So what we did was we averaged several offsets of these blocks. Some blocks would start at 0, 0 at the corner, some would start in the middle. And so we basically smoothed out over many offsets. I think we did about 16. And now Alexandra is gonna talk a little bit about the ice probabilities.
All right, let me just unmute. So originally the US NIC was presented with the CS probability mask, but we decided that a binary mask would be more useful as an end product. So to do that, Mac took the ice probability image output from the CNN and thresholded any pixel values that were above 0.5 in the probability space to be ice, and anything under 0.5 to be open water. In the slide, you can see the sequence of the original input SAR image on the left, the ice probability intermediate output in the middle, and the final binary output on the right. However, there is still a benefit from the probability maps in that it gives us the capability to choose the probability cutoff. So for example, if we believe the probability map better delineates ice, say at 0.7 or 0.4, we have the ability to change that threshold based on each image, which in turn will update or change the final binary image and our end product.
All right. Thank you. And a little bit about the feedback. We wanted to know from an analyst perspective how well our ice maps were performing. And so, you know, we partnered with the National Ice Center, and particularly with Alexandra. We've been very lucky to have her, and she gave us some feedback on the performance of this model. And I'm going to leave it to her to explain the next few slides.
All right, so the binary image seen here with the color overlay was created from a RadarSat 2 acquisition of the city of Acos in February of 2020. To understand how well the binary mask did at picking up the ice from the RadarSat 2 image, I overlaid the original image with the binary image, and I then analyzed the image at the same resolution I would analyze if this were for a US NIC weekly chart, just to get a quick look at how well the binary image did compared to an analyst average analysis. And you'll see at the top an attribute table that's associated with the different colored polygons on this slide and some comments associated with them. Overall, it did a great job on picking up on the consolidated ice seen in the yellowish color that takes up most of the image. Though we noticed within the consolidated ice, the binary image is indicating openings which are not actually there. Looking at the original RadarSat 2 image that was shown on a previous slide, the holes have already frozen over with new ice or ice less than 10 centimeters. It does, however, do extremely well on picking up the detail of the ice tendrils or ice extending from the main pack ice in long strings in the central part of this image. And this is something USNIC analysts could pick up on, but we'd be spending an hour analyzing one image, which just isn't reasonable. So the end goal is the trained model combined with the CIA subject matter expert. And this will hopefully allow for a more accurate, better resolution product of the Arctic that the USNIC can then utilize for daily analysis or a tailored support for vessels operating in and around the sea ice. And with that, I will pass it back to Mac for the next slide.
Thank you. Okay, so we talked about the supervised learning, and let's talk a little bit about the unsupervised. So effectively, in this unsupervised methods, we don't use any labels at all. We use a combination of something called a variational autoencoder. And so what does a variational autoencoder do? It follows something called an encoder-decoder approach, where basically the whole scheme is supposed to take input data and discover some latent state representation of that data. Our input data is the image chip. And in this case, it's a 64 by 64 SAR image chip. And this chip is converted into an encoding vector where each dimension represents something learned about that chip. The encoder network inputs a single value for the encoding dimension, so it makes it coarse or compressed. The decoder and then takes these values and attempts to recreate the original input. A variational autoencoder is different. So it works similarly as an encoder-decoder, but basically the observation in the latent space is more probabilistic. So our output isn't a single value, it's actually a probability distribution for each latent feature, which are features that represent a range of possible values. And so the features coming out of the variational autoencoder were fed into a clustering algorithm in which we decided there would be about 10 labels just to start. And we did this for both RadarSat-2 and TerraSAR-X images, and we'll see them in the next slide. Next slide, please. So the salient features learned from the variational autoencoder were fed into a clustering algorithm called K-means, which I'm sure many of you are familiar with. And as you can see here, we used PCA, principal component analysis, to remap the clusters into a lower feature space. In the figure, in the middle, you can see 10 clusters. We found that this method worked best on the higher resolution images, so on the TerraSAR-X rather than on the RadarSat. And you can see that on the resulting segmented image on the right-hand side, the orange pixels seem to be assigned to like fragile ice. Calm water is assigned to the green cluster, and the blue pixels seem to have areas of higher wind speed. But you know, this is all because we didn't have exact labels for this. This is something that we're still playing around with to look at the metrics. And then next slide, please. And so at this point, we're going to talk about something new. This is an approach that we just started late last year. In engaging with the NIC, we found that, you know, although ice analysts find the completely automated ice maps useful, they would really like more control over the models. For example, to retrain a model on the fly, so on the spot. So we both came up with an idea for a machine learning tool that involves a human in the loop concept in order to meet this need. And this tool incorporates something called active learning. And let me explain how this works. An analyst would ingest a new image in the tool, pictured on the left by that RadarSat image. And let's say that they didn't like the output of the ice map. And they didn't want to play around with the thresholds of the ice probability maps. Let's say that, any threshold they used just didn't work. So through active learning, they can actually retrain a model on the fly without having to label many pixels, because active learning essentially presents the user with the most out of sample pixels, or pixels that the machine found the most difficult to label. And this is shown by that little red box on the radar set image. So therefore, the analyst would just need to label pixels in boxes that the algorithm proposed, as opposed to labeling a large patch or maybe even the whole image, and that in that specific chip. The analyst could be assisted to label by incorporating either clustering techniques shown by that the K-means patch image, or they could use the NIC's weekly ice products shown in the middle. So these would serve sort of as weak labels. We are still trying to assess how the weak labels would work, but we are, very excited about this new project because we are now working directly with Alexandra, who is not only testing the tool, but she's also designing it and working with the computer scientist, and will help us make that tool to stay more relevant to the NIC's workflow. And then I'm going to leave Alexandra to say a few words about this.
So kind of adding on to what Mac already said is the next step will be us at the USNIC to get the active learning tool in user guide. And this tool will be, QC'd by qualified analysts and be used to train the model with SAR imagery. And as Mac mentioned, it will identify patches that the model is having the hardest time labeling, or it will choose patches at random to include a diverse group. This still needs to be looked into a little bit more and decided which way will be the best way forward, which we will do once we get that to the NIC. Mac already mentioned the utility of the different boxes, so I'm going to go into a little more detail on how analysts will use the GUI. The top 3 boxes will serve as a first look for analysts to see how the patch is being labeled, and the bottom middle box will pull in the most recent USNIC weekly analysis to add as guidance to what ice, if any, was in that area most recently. Once that's all done, analysts will go back to the top left box and relabel the patch if it's not labeled correctly. There are different tools seen at the bottom of the interface that will allow me to draw polygons or even partial polygons and to identify where ice exists within the patch. There's even the option to only label a part of the patch if I am not 100% certain of every pixel in the image, because we don't want to label anything wrong and train the model wrong. Once I've labeled a patch correctly, I can then apply my labels and it will update the other boxes and show the updated binary result in the bottom right. Not shown here, but something else that's being worked on is adding they've also added a log that times each interaction within the GUI to use for evaluation later down the road, to compare the time it takes to use the GUI and produce a reasonable output to an analyst's analysis in the final product, to make sure it's useful and also within a reasonable time frame as compared to analyst analysis. And with that, I'll go on the next slide and pass it back to Mac.
Thank you for that great explanation. So we have some new results to show. These are fresh off the press, a couple of weeks old. So basically, we ingested an image for testing that was very different from what we trained our models with. Originally, the models were trained from with images ranging from mostly June to October, early October. And so this February image was a good example to test how good the active learning would perform. So starting with the leftmost plot, we are showing the ability of different models to distinguish between ice and open water. And the higher the number, the better it is. That's portrayed as a rock area under the curve. So each point on the solid and dashed lines represents a model that's been updated with some n number of new samples. So we have two types. We have uncertainty sampling, like Alexandra mentioned, portrayed in blue. This represents a model that updates based on samples that, when run through the model, were the most uncertain. And here, that is a simple metric to determine when the model was most on the fence. For example, if the predictions the most, the probability was 0.5 of eyes or no eyes. With the random samples, yellow, those models represent updates based on random sampling. So the image, basically the active learning doesn't take into account what was hard to label or not. It's just randomly tells you patches to label. And we see the positive impact of uncertainty sampling is greatest with fewer samples, so lower number of patches that you have to label. But the random sampling soon catches up eventually. And about, if you label 50 patches, and it will provide coverage for those uncertain image areas, and then add more diverse samples across the scene. So the purple and the sign circles that are on this graph represent the first instant of the highest area under the curve for each sampling method, meaning the instances where the model had the best performance. And the plots on the right show the ROC curve for these models represented by those circles. Overall, we see very similar performance improvement in the case of when you label 25 uncertain patches and 50 random samples. But we really see if limited labeling time is available, so the analyst isn't rushed, using the uncertainty sampling from the active learning leads to better initial improvement as it targets where the model is struggling more directly. But in either case, fine-tuning the model with a relatively small number of labeled patches enhances performance. So we do know that the active learning is working, and it's working very well. Next slide, please. And finally, I just wanted to recruit people in this slide. So we have several programs at NGA, and you know, so we have pretty exciting research programs. We have great partnerships. So we hope that maybe the younger crowd might want to look into IC postdoc fellowships, visiting scientist programs for starting, middle, or even late career scientists can, and also please make note of our CRADAs. We have CRADAs with universities, with businesses. So these are really great programs. And of course, we have the NURI, the NGA University Research Initiatives, that we put out for calls for different research programs. So definitely be on the lookout for these. And with that, if Alexandra has anything to add, I'm done with my part.
I'm just going to put a shout out for our new website, usicecenter.gov. I'm going to put it in the chat. It's much more user-friendly if you want to check it out. But besides that, that's all I got. Thank you.
Are there any questions?
I have one. This is Twyla. Hi, nice to meet you all. I'm one of the scientists here at NSIDC. This was all super fascinating. And in part, I'm working on a project right now where we're understanding how polar bears use the Southeast Greenland environment. And so we had hoped to use actually calibrated backscatter data ourselves for looking at sea ice conditions in the Greenland fjords. And so those are, of course, areas, you know, they're not usually part of any kind of sea ice product. They're they're just too close to the coast. But we found some difficulties too with the backscatter data having, instances maybe from wind or other things where, one day a surface is bright, another day it's dark, but it seems likely from looking at optical or something else that actually it's the same surface essentially. And I'm wondering if you've run in, well, I have lots of questions, I admit, and I won't ask them all. But I'm wondering if you ran into some similar difficulties with the backscatter and kind of found ways to help overcome just some of that behavior as far as getting kind of different scattering from similar surfaces at different days. And I'm also curious whether you might be, as you're putting together your product, et cetera, how close you're going to get to coast since you're working with some pretty high resolution imagery, certainly more than kind of some of the classic, passive microwave or sort of things like that we use for sea ice.
Yeah, thank you for your question. Can I ask what kind of SAR sensor you're using?
Yeah, so we had been looking at Sentinel-1, and so really it's definitely not some of the resolutions that you've been chatting about, more like 50-meter pixel resolutions.
Okay, yeah, we are also aiming to use Sentinel, so I'll definitely keep you updated about that. I'll put my email in the chat at the end, and so you can definitely reach out to me. But yes, to answer your question, wind tends to be an incredible confuser when you're dealing with sea ice, and sometimes it flips the signature. Sometimes the sea ice will look black, and the open water will look almost white. And so there are algorithms out there. I believe that Noah, and I believe that Alexandra can speak about the wind vector. There's some products that Noah is developing, but we are looking into adding wind vector measurements into our models. So to add another dimension of flavor to the image, that is one way that you can sort of look into that discrimination. I can't really, tell you for sure that that'll help. And then certainly there are ways that you can leverage polarimetric decompositions in SAR imagery, such as taking maybe ratios of horizontally receive with vertical receive, maybe a vertical, horizontal. There are some literature that say that you might be able to sort of offset those confusers. But I think you're doing the right thing by implementing like radiometers and optical, because at the end of the day, the more data you have is the best. But I'll leave Alexandra to talk a little bit about the wind.
I was actually looking for the website that pulls wind vectors from the SAR imagery, and once I find that website for you, I will post it in the chat for you to be able to utilize.
Great, I really appreciate it. Yeah, also because it seems like to some extent kind of being able to introduce time series also very helpful, but of course that's challenging with a lot of machine learning techniques.
Yes, yeah, it's a struggle for sure.
I have a question to, if no one is going to ask. I'm Behzad. I'm a PhD student at CU Boulder, working on a project actually very similar to yours on Arctic sea ice classification. And I have a few questions. First, in the active learning tool, the images that you use, are they RadarSat images or TerraSAR or something else? And then the sort of the underlying algorithm that you use, because you mentioned these are patches of images. Is it using UNET behind the scene, or is it another algorithm in use in there? And then the last question I had is if these results are published or are going to be published anywhere in this time soon. Thank you.
Thank you for your question. Yeah, so the initial model that I showed you with the active learning is using RadarSat 2, but we are going to implement a model that uses Sentinel. to answer your question about the UNET being in the back end of the active learning tool, yes. However, it's, you know, if we're introducing an image in the active learning tool and we classify it and we kind of like the results, but there's some patches that, you know, that you didn't like, you can remember the sort of the architecture and the training from the UNET, but you are also able to forget the labels that you trained it on. So essentially you're retraining a whole new model on the fly. That's going to take a little bit of time. We're still looking into the processing times of what that would do to just doing one image. It may take, it might not be 5 minutes, because with the UNET right now, it's under 10 minutes to get an image classified whole. But to do it on the fly, that it may take like 10 minutes, 12 minutes, or something like maybe 20. But it's certainly not going to take hours or anything like that. And then your question about publishing, we are aiming to publish the work that you saw with the ICE probabilities. That's going to hopefully get, you know, if they accept it, into IEEE. So we should be submitting that in July. And then we are aiming to write another paper about the active learning, which we aim to put into the Geophysical Research Library journal. And then we're going to be writing that with Alexandra. All of these two papers are going to be writing with Alexandra and some of the leadership at the NIC as well.
Thank you very much. Appreciate it.
Hi, this is Andy Barrett. I'm working with Bazat and also Morteza Karamzadeh on a very similar project funded by NSF EarthCube. But I had a question for Alexandra. How long does it take an analyst to analyze a single image normally? What amount of you said you needed to do your analysis in a timely manner, and I was wondering kind of how much time do you spend on a single image, and then what is the advantage that you gain from using this active learning approach, or even just the machine learning classification?
Those are two very great questions. So to address the first one, so we are in charge of analyzing the entire Arctic and Antarctic on a daily basis. And there's only so many of us, there's only so many hours in the day. And I would say, I know more of approximately, we analyze 40 SAR images a day for our daily analysis. And this is based on our drawing an ice edge and a line that delineates the 80 to 100% ice. And so we don't necessarily need the 100 or 200 plus sentinel images that are produced daily, because that's in the pack ice and that's not where we're concerned with for our daily analysis. So yes, there are more images, but we don't necessarily need to analyze that for our daily analysis. So for about 40 images and 2 to 3 analysts working on that, it takes approximately 4 hours to complete just the Arctic analysis and Antarctic. To answer your second question about how useful this would be, a good example would be for one of our missions. They like to retrieve buoys in an opening within the sea ice. And while we do provide tailored support that we do give more in detail, this would be a rapid way to quickly show, here's where the current openings in the ice are. Okay, we're going to be here in 2 to 4 hours. Where do we think the ice is going to shift, and where do we think that hole is going to be? So it would just be a quicker way to turn around versus an analyst spending an abnormal amount of time on one image. So hopefully that answers your questions. Let me know if you have any follow-on to that.
Yeah, great, thank you very much. It does.
This is Sergio. I have a question. Thanks, Mac and Alexandra, for both of you for very interesting talks. And my question, I guess, is for Mac, and I might be slow here, but is a model trained on one image used for other images, or are you train the model on every image, a new model for each image?
So that depends. That's a good question. That depends. Right now, you have the ability to either forget or remember, depending on the results that you get. For the probability ice maps that I showed in the beginning, that's trained on 130 images, where you take 2,000 chips of those 224 by 224, and you create a unifying model. For the active learning, though, that depends. If you don't like the results from the probability from the, let's call it the OG model. If you don't like OG model, then you would essentially either remember some of the labels, or you can forget all the labels you've ever seen and just create a new one on the fly. So it really depends on the output of the result, and according to the analyst.
So this is just one analyst? I mean, is the model generated in the active learning, is that just following one analyst through his workflow for one day, and when he or she comes in the next day, they start over, or does it remember the model from the day before, or?
Yeah, so we're looking into how to essentially save models, and that's easy to do. You can just save the model and then sort of incorporate it, bring it back, and use the pre-trained models. That's not a problem. So if an analyst wanted to start fresh, they just start fresh, and if not, they just they incorporate the models from the day prior, or they can do a mix. They can essentially bring labels, and they essentially will take a pre-trained model from yesterday, let's say, and update just a few patches so they can get their desired result.
Are models shared between analysts?
That right now we're in a level 0 prototype. So that's actually a nice idea that you brought up. That might be something that Alexandra along the way will have to test out, and because maybe they don't want to share, maybe they do. Sometimes analysts will have a different interpretation of what an ICE type is versus another ICE analyst. So that's definitely something that is trial and error, I think. But a good that you brought it up. Thank you.
So is there scoring done, through time? Can one model be shown to be better than another model if they're being done by two analysts, or are there ever any sort of cross calibration where all your active analysts analyze the same scene and you compare what they come up with?
Yeah, certainly those are things that, because it's not even an early adoption, this is a prototype. Those are things that have to be discussed by the analysts along the way. So this is what you see now, this active learning tool. It's currently being, every month we're updating it and we're supposed to give it to Alexandra about the end of this month, the latest. But I'm hoping that more analysts will want to adopt it and will want to play around with it. But right now, it's going to be just Alexandra sort of navigating it. But yeah, we're hoping that the analysts will want to speak to us and say, hey, can you add this? Can you remove that? We don't like that at all. We don't like this button here. It's annoying. Things like that.
And to kind of add on to what Mac just said is, when they first showed it to us, I had a meeting with our operations department and analysts to get their input, because I mean, more ideas are better than just one. So I'm going to continually involve the analysts to make sure everyone has a say, and it's not just me who has a say in what happens to this. So everyone's invested in this tool.
Great, thanks.
This is Walt Meyer. I'll kind of follow on from Sarah Joda's question. First, I'll mention kudos to Alexandra and the NIC team for the new website. It really looks great. It's great to see. I used to work at the NIC over 20 years ago now, and the website is improved a lot. And so nice to see that. And as a question, kind of more of a specific, if you mentioned this, I missed it, but one of the challenges with with microwave in general is the melt season. Is there any thought towards, I mean, is this just not useful during the melt season, or is there potential ways you could adjust the training or do training specific for melt ice? Because that's obviously an important time of year.
Yes, so I did train the model to be closer to the melt season than the freeze. So we train models with imagery that come from June to the beginning of October. However, we didn't have a lot of imagery in our library that were from October to May. We were lacking. And so that's why we built the active learning tool, because we knew that we wanted to be able to still classify imagery, even though we didn't have labels for those type of images. And the best way to do it would be to give it off to an analyst who know about how to label this, but give them something that they wouldn't have to label for hours and on end, because it's very costly to label specifically pixel. By pixel level takes a long time. And so essentially, to answer your question, our original model is trained on the melt season. But if we didn't have that, you could still use the active learning tool to create new melt models with relatively little amount of labeling.
Okay, thanks.
You're welcome.
Any more questions? Obviously, this is a very keen interest to NSIDC. I think you can tell that. Other questions? There's Florence.
Yeah, this is Florence. Hi, it was great to see this talk and to see how far the research has come. It's terrific. And I just wanted to remind everybody, I put a link in the chat box for, it's a version, I'll call it, of the weekly products that Alexandra mentioned that were used in the study. The version that we have is a compressed version of the information in the weekly charts and in NetCDF. I just want to share that information because I think it'll be useful for other research projects.
Thank you. But yeah, just a last word is, you know, if you guys feel like you'd like to collaborate with us to also get the tool, maybe use it on your own end, train it, and give us some feedback. That's something that we can do. There, you know, with NGA, there's a little bit of the security process takes a little bit of steps to ensuring that we are able to give it to you in a manner that's acceptable to the agency, but that this is unclassified work, so this should be relatively easy to do. And so, you know, definitely reach out to me if you want to be a potential test user of the tool.
Anything more from anyone? This has been great. Clearly, we think similarly. So, all right. Well, if there's nothing more, this has been really good. This has been really good, very, very informative, and you know, clearly we're very interested in this sort of stuff and machine learning and all that. So, if there's nothing more from anyone, then I'll thank Mac and Alexandra for a wonderful talk, and we'll go from here.
Thank you.
All right. Well, thanks everyone. This has been great. So.
Thank you so much.